Hey guys, so what I wanted to look at in this first free response breakdown is this guy here, 2008 Form B, all right, free response question. Okay, all right, so we take a look at this one. All right, first thing it says is answer the following questions regarding the decomp of ASF5. And it says that we've got 55.8 grams of it in a 10.5 liter container at 105 degrees. And it wants to know what is the initial molar concentration of the ASF5. All right, so in part A here, subset I, if I want the molarity of ASF5, there's two things you need. Got to get the moles of it. Got to get the liters of it. All right, so if we take a look, right, the liters is easy enough. They told us that we've got a 10.5 liter container. Right, so you're halfway home there. All right, and our moles of it, they don't give us the moles, but the next best thing's there. They gave us the grams of it. So what you want to do is take your 55.8 grams of the ASF5, and we can use the periodic table to convert our grams into moles. So if we go and snag those numbers, fluorine is 19.00 times the 5, right, plus the AS. Take a look to find the arsenic. That's 74.92. All right, so it looks like we get 169.92 for our grams there. So do that conversion, 55.8 divided by the 169.92. That gets us 0.323 moles, and we plug that in up here. All right, so it looks like we get 0.0308 molar ASF5. All right. Then in B, or rather A subset I, they want us to find what's the initial pressure in atmospheres of it. All right, so can't be like a partial pressure where we're subtracting because they don't give me any pressures. All right, so you start thinking, how else could we get pressure? All right, and I've got moles, and I've got liters, and I've got temperature, and all of that hopefully feels like a PV equals nRT problem. So if I want the pressure, I will take nRT over V, and we plug some values. Now be careful, my moles is the 0.323. Don't just grab your final answer. 0.323 moles times your constant R, which is 0.0821 liters ATM per mole Kelvin. Temperature, just have to make sure it matches your R unit, so it's got to be in Kelvin. They listed it in Celsius, so we're going to have to take our 105 plus the 273.15 and stop that number at the decimal. Feels like 378. On the bottom, we have our volume, which is our 10.5 liters. So moles goes, liters goes, Kelvin goes, and now we just do some math. All right, so if we're looking at the pressure here, it feels like 0.955 atmosphere for this. Then we push into the next part of the problem. All right, if we do that, all right, they tell us we've got this equilibrium listed, the ASF5, going to ASF3 and F2. It says in terms of molar concentration, write the equilibrium constant expression for the decomp. So all they want for this is a K expression. All right, so if I'm going to write a K expression, K expression is products over reactants to the power of their coefficients. Don't forget, omit pure liquids and solids. So we're looking at ASF3 and F2 on the top, and our ASF5 on the bottom. Right, so there is your K expression. All right, C says when we get to equilibrium, 27.7% of the original ASF5 moles have decomposed. Calculate the molar concentration of ASF5 at equilibrium. Right, so if we want equilibrium concentrations, the best way to get those is by doing an ice table. Big common theme in this chapter. So you start with your equilibrium, the ASF5. We're going to ASF3 plus the F2. Set up your ice table. Our initial concentration of the ASF5, we calculated it over here. It's the 0.0308 mole. They didn't give us any information about the initials of these guys, so you can assume them to be 0. We know the reaction's always going to proceed toward the 0 because if you do a QK analysis there, it's always going to lead you to Q is less than K, so it'll be a shift right. All right, that means my change line is going to be minus X, plus X, plus X. And then my equilibrium line, 0.0308 minus X, X, and X. All right, next thing we always do is plug into our K expression. So we'd say K is equal to X squared over 0.0308 minus X. But once we get here, you run into a situation where I don't know K and I don't know X. And whenever that happens, I always say there's another bit of information listed to help you get X somehow else. All right, so we start scanning, and sure enough, they tell us some stuff about the ASF5 at equilibrium. At equilibrium, right, with the ASF5, they're telling us we have 27.7% of the original number of moles of the ASF5. So that means, right, that 27.7% of this has decomposed. And whether you do it here or here, you'll get the same thing. Now be careful, right? That's not telling you how much is left. It's telling you how much went away. So the first thing I'm going to do is figure out how much is left. Right, so if it's 27.7, right, just checking that number. Right, so we take 100 minus 27.7. That means 72.3% is left. So if I take 0.723 times the 0.323 and divide it by the 10.5, I get a value of 0.0222. If I just took the 0.0308 times the 0.723, I get the same 0.0222. So either way, you can just simply take 72%, right, of your molarity. So I know, right, that 0.723 times my 0.0308 is equal to 0.0308 minus X. And now I can solve for X in a different fashion. So like I said, your 0.723 times this is 0.0223 molar. And that's equal to 0.0308 minus X. Do some math there. So you subtract the 0.0308 over, right, and we get negative 0.008 5 equals negative x. So my x is 0.0085. All right, so that's what they wanted there. They wanted the molar concentration of the ASF5 at equilibrium. And you already got that right here. I went ahead and solved for x because sure enough, in the next question, for letter C, they want you to solve for K. So if we're going to do that, I'm going to take my 0.0085 squared over my 0.0380 minus 0.0085. And if we do that, I get a value of 0.00324 for my K value. All right. Last but not least, all right, letter D. It says calculate the mole fraction of F2 in the container at equilibrium. So that's a bit of a throwback, right? We did mole fraction a little bit ago, but remember, mole fraction, right, is abbreviated with a big X of F2. It's simply moles of the little over moles total. Right? So you have everything you need. You have each of these values for their molarities. You just need to make them be moles, all right, to do that. All right, so if I do that, right, I know that F2 is equal to X. Right, but you got to be careful, right? If this is 0.0085 molar, I have to use the 10.5 liter container to convert it into moles. Right? So if I were doing that, I would simply take my 10.5 liters times my 0.0085 moles per liter to get my moles there. So 0.0085 times my 10.5. Right, so I get 0.0893 for my moles of F2. Right, so there's my numerator. And now I'm going to get the total moles. Right? So good news. Right? On that front, you know the ASF3 is the same value. All right? So on the bottom, I'm going to have the F2, the ASF3, and the ASF5. Two of those values are going to be the same as this. Right? So that one there, 0.0893 plus 0.0893 plus, and now we just need to figure out this guy here. So you know what he was at equilibrium, the 0.0223. You just have to make it be moles by timesing it by the 10.5 liters. You do that upright, you get 0.234. And then you do your math to finish up. If you do that up, you're going to get 0.216 for your mole fraction. All right, so majority of the problem there, a lot of ice table stuff, right? Little wrinkle there at the end where you do the mole fraction thing. And then, like I said, be careful in here. This is one of those, I have other info that lets me get X a different way styles, which we've been calling style 2 as we go. All right, so hope that helped you out. Let me know if you guys have any questions.